Hello, I'm Xu Weiqing, a PhD student in University Gustav FA. My topic today is about knowledge graph management on the edge. Here is an outline of my speech. First of all, I'm going to talk about RDF edge computing. After that, I will give an introduction of succinct data structure and the wavelet tree, which is used as basic data structure of our system. Then I will introduce Lightmat encoding, which serves as rapid RDFS reasoning services. After introducing all these concepts, I will show you the architecture of our system, succinct edge. Together, I will also show you the core processing and optimization of our system. After that, I will give an evaluation of our system comparing with other RDF systems. And finally, I will give the conclusion and perspectives. So, what is edge computing? Edge computing is a processing paradigm that brings storage, management, and processing of huge amounts of data closer to location where it is need to be performed. This means the highly local context-aware and responsive services are required, which can eliminate the data round trip to the cloud. Considering an RDF system for edge computing, some requirements must be satisfied. The first one is this should be an in-memory system which can reduce the read and write of disks. Second one is that this system should have a compressed single index storage which can reduce the memory footprint. Third one is that this system should support the decompression-free operations, which can accelerate the core processing. The last one is that this system should have adapted core processing with reasoning services. Based on this requirement, succinct data structure will be a good choice as a basic data structure of our system. Succinct data structure is a family of data structure that stores data in compact way but still allows efficient data access operations without decompression. This kind of data structure supports three different decompression-free operations which allow to retrieve information. They are rank, select, and access. Rank serves as retrieving the number of occurrences of an element by giving a position. Select serves as retrieving the position of an element by giving its ordinal number. Access serves as retrieving the element by giving a position. More precisely, we use wavelet tree as a basic data structure, which is the data structure of succinct data structure family in our system. Another important concept must be introduced is Lightmat encoding. Lightmat is a semantic-aware encoding scheme that compresses RDF datasets and supports reasoning services associated to RDFS ontology language. The main idea of Lightmat is the top-down encoding of the concept and property hierarchies, where each subconcept inherits the identifier of its superconcept, respectively the same manner with properties. By using this strategy, we can easily retrieve the hierarchical information directed by calculations instead of searching into the T-box. Here is the architecture of our system, succinct edge. The whole system is composed by four main parts. The first part is the query engine, which serves as processing the SPARQL query. The second part, dictionary, which store the mapping between all the RDF elements and their corresponding identifier. This is where the Lightmat encoding is implemented. The third part is RDF type store, which store all the triples with RDF type as a property. The fourth part is the triple store, which store all the rest triples. We had distributed these triples to two similar data structure, relying on the type of object, which means the data type object or the instance type object. Once a Sparkle query comes, the query engine first translates all the RDF elements to their corresponding identifier with the help of dictionaries. Then, the query engine sends the translated triple pattern to RDF type store or triple store to get its corresponding result, and does the join work with the temporary result set. After all the join works are done, the query engine will output the result. This is the inside view of the data structure in the triple store. We have stored the sequences of predicates, subject, and objects in form of the wavelet tree. Each two layers are connected by bitmap, which links an element to a subsequence of elements in the next layer. The evaluation of our system is conducted on Raspberry Pi 3B+. We have compared our system with RDF4 LED, Apache Jena, and RDF4J in aspects of database construction and query processing. This figure shows the comparison of database construction time. We can see from the figure that with the growth of datasets, succinct H gradually outperformed the other system. If we compare the memory footprint without dictionary of these systems, we can see that succinct H take much smaller memory space than Jena TDB and RDF4 LED. As for dictionary size, succinct H also shows its advantage compared with Jena TDB and RDF4 LED. In the experimentation of query processing, we have executed several queries without the requirement of reasoning services with these systems. We can see that in most cases, succinct H outperformed the other systems. As for queries which demand reasoning services, we can see that succinct H still shows its strength compared with other systems. Here are the conclusion and perspectives. To our best knowledge, succinct H is first knowledge graph inference-enabled data management system designed for edge computing. It is relevant for many Internet of Things use cases, such as anomaly and risk detection, supervising energy production and distribution. In the future, we're going to improve join ordering and ontology expressiveness. We're also going to extend succinct H to a distributed approach together with the support of data streaming. Thank you.